Okay, so thank you, John Tip, for the introduction, and thank you everybody for joining me this morning. So as John Tip mentioned, this is a talk that's kind of combining a lot of things, including quant control, including machine learning and control engineering. So because of that, if anybody has any question or something is not clear, please do interrupt. Because I would rather that everybody follows to a certain degree than we go through all the talks and then nobody follows kind of 2/3 of the way through or 1/3 of the way through. And just to be clear that although I've been a postdoc at Warwick for some time, this work is actually the work that I've done during my PhD. So it's a bit outdated, I would admit. And if if you're not familiar with where University of Calgary is, so that's where I did my PhD with Dr. Barry Sanders, that's the map for reference as to where Calgary is. So that's kind of middle nowhere, Canada, right up north from the state of Montana in the US, if you kind of know the geography of the United States. So this work is also done in collaboration with Dr. Peter Wittek, who supervised the kind of the machine learning and the computer science part of the project. Unfortunately, as some of us know, he's gone missing since his Himalayan expedition in the late September last year. So we're still kind of hoping that we will hear some news about him. Nothing yet so far. And since I've mentioned we're covering a lot of things in this talk. If you're interested in the result, or if we did manage to get through all the talks today, these are 3 main references. If somebody wants to screen cap those references or take a picture, those are the references you can go to at the end of the talk if you're interested. All right, so let's get to it. So it's kind of the basic for people who might not be familiar with quantum control. So the terms kind of got coined in the beginning for quantum chemistry, really, as a references to the control of chemical reactions. So at the beginning, it's a reference to the control of the quantum state of light that they use to kind of catalyze the state of the molecules or the ions, so that they would get an increase in the chemical reactions they're looking for. And if you look in the literature, there will still be papers that use the term quantum control kind of exclusively in that way. But because the applications of quantum control now kind of extends into the field of quantum computation and more kind of specifically to this talk, quantum metrology, which we'll talk about later on in this talk, quantum control now kind of refers to the steering of the quantum dynamics through any kind of available controllable degrees of freedom that we have, so that we use kind of a desired observation from the system. So that's typically done by designing what we call a control policy. So you can think of that as either a set of rules, or you think of that as a program, so that if you have a controller that's going to react in either time or react to an outcome of the control system, so that you get to the desired quantum state or desired observation that you want. So typically speaking, how you do that is you devise it from the quantum dynamic, from a model of the quantum dynamic. But if you're relying solely on the model, there are some limitations to that. It works very well so far, but if you're trying to scale up the quantum system, for example, you can run into a bit of a problem. For example, if the systems becomes large, then complexity starts to kick in. If you kind of try to think of it quantitatively, if you think about it as in metrics representation, for example, and you try to represent fully both the dynamics within the subsystem and entanglement between the subsystem, then the metrics representation, full size in metrics representations would scale exponentially with the size of the full system. Let's say if we have n qubits, then the full size of the metric representation is 2 to the power of n. So that is huge. So if you're trying to devise a policy, let's say using a Hamiltonian that is that size, you can kind of see the challenge that comes out of that. There is also an issue of whether the model is accurate enough, and I have to kind of put the quotation mark on top of that, because there's always a question of when is the model accurate enough. There is not a good way of quantifying that unless you actually test the policy that you get from that model. And if you imagine, if we're trying to scale up, then there's crosstalk noise, and there's other imperfection that comes with trying to engineer a large system. And the question of accurate enough becomes even harder to quantify in that sense. So if we're thinking practically about trying to get towards a quantum technology that is going to really matter, in the sense that we're trying to really being useful in comparison to a classical technology, then having a quantum control that's kind of gets stuck solely on devising based on model might be holding us back. Well, how can we kind of try to get over that? Well, if you look into classical control engineering, they're also stuck with the same problem, because they're also devising things for large system without accurate enough model. And the way they do it is they kind of look into how they can use data to improve the way they're devising their policy. So that's the first part of the talk I'm going to give today. So how can we kind of quantize the way we do the way we make control policy? Then in the second part of the talk, I'll walk you through an example of what of a control problem that I did during my PhD, which is the problem of adaptive quantum enhanced phase estimation. So that is one of the problems in quantum metrology that people look into as an example problem. And this one is particularly interesting because it's adaptive, so that means we have measurement involved in there, and because we have measurement and the outcome is actually random, then there is an added complexity of how do we respond to the measurement outcome in a way that will actually get us to the precision that we want. Okay, so let's start with how do we get a data-driven quantum control. So to try to get to a framework for data-driven quantum control, we kind of have to start with formulating the framework for a quantum control in the way that a control engineer would actually do. So if you open up a textbook for first year control engineer or like introductory course for control engineer, you kind of have to start with this diagram. So in the most abstract sense of the control system, you would have a controller. So you can think of it as a kind of a very specialized computer where you have a program, which is the control policy. And this computer, the only thing it does is it takes in your control goal, and then it also takes in the signal from the plant, the signal from the measurement of the plant, and then it uses that program to try to compute out what signal it has to give to the plant, so it can get you to the goal that you want. And then the other block in this abstract diagram is the plant that you want to control. So in our case, in quantum control, the quantum system we want to control is inside this plant. So we kind of squash everything into this plant. So the measurement system is also inside there. The oscillatory system that we use to interact with the system is also inside there. And then we have all these channels that communicates between the control and the plant. Although if it's the classical case, then all these channels are classical. But if you go to quantum control, now we have to start to think which of these channels do we allow for quantum information to be transferred in between. And as of now, what seems to make sense is to have the U channel, so that's the signal going in between the control and the plant. That is probably okay to have quantum information going through, and then the feedback to have quantum information going through. It's not very clear from this diagram, but the feedback can also be classical signal. So the purple means that we're allowing for quantum information. It can also be classical information, but the orange is kind of strictly classical information. So now once we have that, so this is kind of a review for like the general procedure for devising policy from a model. So of course, first step, if you want to devise policy from a model, you start with creating the model. So typically for us physicists, we start with creating the first principle model. So that's when you start with the physics of the plant. So you know this is a quantum system. You start what type of quantum system, what Hamiltonian, do we have decoherence, what kind of noise is it, did we write down the model? But in general, that might not be the information that's available. So if you're an engineer, maybe instead you would look at the input-output data of the plant and then instead write down what is a mathematical approximation of the response of the plant. So that's another way of doing it. It might not be as informative as the first principle model. That's why we kind of favor first principle model. But that's also something that they do.
Can I ask a question?
Yeah, sure.
So when you say P and you have like F and rho, are they related in some sense?
Oh, the F of rho in the second, the performance.
Yeah, so like I have P and rho. So rho would be the states of what?
Oh, the rho in this case, squiggly rho is
the barrel,
the control policy. So it's the one inside the controller.
So it's like a setting of C?
Yeah, it's the setting of C.
Okay, so F would be any functions of performance.
Yeah.
So that's kind of strange why it doesn't relate it to P at all then.
It's not explicitly stated as relating to P here, but it is.
Oh, okay.
So it depends on what you're controlling. So yes, you're right. It's related to P. It's just not stated at all.
Okay, thank you.
Yeah. So as mentioned, that's kind of the second step is you have to define what kind of performance you're looking for from your control system. That's going to include your P, your plant.
I have a quick question on this slide as well. So it seems that the output of the plant is both Y and Z. And you say Z is a classical channel, which in some sense you can measure, but then Y would be feedback into the controller. So in this case, what is the actual measurement that you make to see if the control policy is working well? Is it C? How do we monitor this cost functions or performance function?
Okay, so because this one is kind of an abstract diagram, I didn't really specify. But I would say it can be both, depending on your problem.
Okay.
It kind of depends on the specific things.
Okay.
Depends on what your Z is, depending on what the Y is.
So is the eventual goal is trying to measure Z that reflects the optimal control policy?
That is one way of working Z, of using Z, yes. That is actually the way you use it.
Okay.
In the adaptive phase estimation. Spoiler alert.
Okay.
Oh yeah, so like Z is like an output of something that you want at the end.
Yeah.
Okay.
That's kind of why we split those two channels from each other as well. Like if you look at like some of the textbooks for classical control engineering, it comes out as one channel and then they split it into two. Which in quantum control, it might not make sense.
What do you mean splitting like Z?
They have only one Y coming out and split it.
Okay, I see.
Yeah. If we were looking at that, it's like in quantum control, this might not be what you're looking at all. So that's why we explicitly split this into Y and Z.
Okay.
Mm-hmm.
Thank you.
Okay.
Yeah, okay. It might be clearer once we get to the example. Because this is kind of very abstract at the moment.
All right.
Okay, so once we have the performance function, and then the third step would be to, now that's the optimization step, because now we have the performance. Now we can find the policy that according to the performance would be the optimal one. Okay, again, these are all very abstract, and that's because once we have that, now we can kind of draw where the data-driven control loop is going to come in. So in data-driven control, the idea is that we're going to skip the model making part, so the first step, and kind of use the input-output data from the control loop to go directly to making the control policy. And they do that by adding the supervisory control, or in the older literature, in the field, they call it the learner, and then kind of draw all this channel that takes in the data. And
sorry, just a little bit. It would be helpful if you could use a mouse to kind of like go over the places you're talking about. Yeah, that would be helpful.
Yeah. Okay, thank you. Okay, yeah. So the supervisory controller would be, or the learner would be sitting separately from the control loop here, and then taking in the data that's going into the control loop, and then what the learner does is it's decide how it decides on how good a policy is, and then modifies the policy until it gets something that, now in principle it gets the optimal policy, but that depends on the kind of optimization algorithm or the learning algorithm that you use for the procedure. So in principle, data-driven controls try to do it model-free. It doesn't necessarily have to. Model-free and model-based is kind of, you can think of it as something on a spectrum. So on the one side, you do it completely model-based. On the one side, you do it completely model-free. But there are also techniques that exist in between where you're trying to incorporate some of the model and also use the data to have both the flexibility and kind of the knowledge from people who already know the dynamics inside the plant. So you kind of reduce the need for the data, but also have some of the flexibility. And I should also emphasize that doing it model-free doesn't mean that we have no knowledge about the control system, because we still need to know what kind of controllable degrees of freedom exist in the plant, and also what makes sense to control, what makes sense to measure. Otherwise, the control loop would not work. So the model-free only refers to the fact that we're trying to skip the model making step. That's all. Doesn't mean that we can go into this completely blind. Okay. Again, all this might be a bit clearer if we look into a specific example.
Well, one particular note on terminology I find is quite interesting, is that the learner and supervisor are the same entity, which is usually not the case for standard feed-forward neural networks or supervised learning, right?
Yeah.
So you both learn and control at the same time. It's kind of funny.
Yeah, that might be why they now shift to the terminology of the supervisory controller.
Right.
Sure. Learner is a very old terminology. It's like
I see.
Early 70s. I don't see this anymore.
I see. Okay. Thank you.
Okay. So the specific problem that I looked into, as I kind of briefly mentioned, is adaptive quantum enhanced phase estimation. So before we talk about the quantum enhanced part, let's just talk about the adaptive phase estimation part, which is kind of what's existing inside the plant P. That's inside the diagram before. So the aim of the adaptive phase estimation here is to estimate an unknown phase using a quantum state of n particle. So the particular setup that we're looking at here is a Mach center interferometer. So in one arm, we said there's an unknown phase. In the other arm, we put in a controllable phase shifter. So that's our controllable degrees of freedom. And the way we use the state of n particle here is that instead of putting all the n particles through the interferometer all at once, as most of the time we would do, we split them into a train, and in each time step there's only one photon or one particle going through the interferometer, and then the path of that particle is detected at the end, and that path we code it as either 0 or 1, and that's what the controller, that's the data the controller is getting as y here, and based on that data it decides on the changes what it wants to make on the controllable degrees of freedom here. And so each time the particles goes in, it makes a slight change to the controllable phase shifter, and once all the particles goes through, then we make an inference about the unknown degrees of freedom based on the value of the controllable phase shifter. So that's the idea of how it's done. So if you so wish to write down the model of this dynamic, now you have an idea of how to do it.
So sorry, just want to make sure that I understand that. What's the meaning of the blue arrow?
Okay.
Because like there's the one that goes from E, which you didn't talk about, but it goes to the phase phi, the unknown phase phi.
Yeah. So
it goes from E to C. Yeah.
So the orange arrow here is it's the feedback loop. So so that happens for the duration of one state. So the blue one is the one that happens for every episode.
You say episode?
Episode, yeah. So because I kind of didn't talk about this, because what this E does, it actually calculates the statistics of the estimate that we infer out of the controllable phase shifter here. So we have to collect a lot of inference. So we have to run this for a lot of episodes.
Oh, so the blue line from E to phi, or the one below, yeah. It's just like to estimate the phi. It's not like there's nothing sending. Yeah. There's no sending information to phi. It's just to estimate the phi. Is that right?
So with this one, we're kind of saying, well, if you're training, so if there's a kind of training of policy, then there may be a signal sending here.
Okay, sure.
So if you don't do training, then you don't need a line there.
Okay,
that might be any kind of random find you're trying to estimate.
Yeah. Just want to compare with the previous diagram of CP and the output Z. Now it seems that we don't even make a measurement Z, or maybe you're missing the arrow on the top left corner where you actually make the measurement. But now this quantum measurement also feedback into the P, which is, I think, got me a little bit confused with the previous diagram when the output of P is actually just Y and Z. Now it seems like P has its internal structure of measurement in there.
Actually, what we kind of didn't really go into is that P is allowed some kind of internal structure. It's just that for the purpose of making it simple, we didn't really draw anything.
Okay.
Here.
Okay.
Yeah.
All right.
This is kind of like the absolutely the highest, the least abstract kind of way of drawing a control.
Okay. Okay. I see.
Yeah.
Thank you.
Yeah, but usually P would have some kind of internal structure. Okay, any more questions, actually, because this is kind of the more complicated picture.
This is interacting or non-interacting?
Which part?
The psi n.
Psi n.
The quantum state. The setting. What is the physical system we're talking about? Is it
probably
like
photons?
So non-interacting?
Probably. Because otherwise you cannot make the measurement like one at a time. I think. So you have to assume like independent states, right? For like n particles.
Oh, you mean
like no interactions between the n particles of what he asked.
Okay. So in my work, I've tried simulating both actually. Both n photon as independent particles, like product state, and n photon as entangled particles. So the entangled particle are not realistic state to generate at all. We just want to see what happens.
Wait, you say that you can do it for the entangled state?
In a simulation. I actually did discuss this with experimentalists, whether it is at all possible to kind of have a train of particle that maybe have more than 50% probability of having photons in each pulses and entangle them together, and we couldn't figure out how. So realistically speaking, not possible. Theoretically, a good thought experiment.
Okay.
Although during the discussion, it comes up that there might be interesting application if it is at all possible to generate. Nobody knows how yet.
So the performance function in this case would be how different a big phi and the psi is. Is that right?
That is one possible performance function. The one we're more interested in is actually the scaling of the uncertainty, and there is a reason to that. And that comes from the field of quantum enhanced metrology. And that's because if you look into statistics and you try to, like from central limit theorem, if you repeat your measurement, you will get smaller and smaller uncertainty depending on how often you do the measurement, and that scaling is always 1 over square root of the number of times you do the measurement. And in the case, kind of tying back to what Tu was saying, if we're doing that measurement, let's say with product state, and you think of what we're doing as every time we're tweaking that controllable degrees of freedom, we're making a guess on what the unknown parameter is, then that scaling the scaling that we'd be having would be 1 over square root of n. And that's known in quantum metrology as the standard quantum limit. So a product state would give you that. But it has been shown that if you use entangled state in kind of this particular setup, what you would get is you can actually improve that scaling, fixing the n to 1 over n. So that's kind of quadratic improvement. That's known as the Heisenberg limit. So that's kind of where in quantum metrology people are trying to aim for. So can we devise something that breaks the standard quantum limit and aim to get at the Heisenberg limit, if at all possible?
So P equals to 1 is the maximum power that we can get for this kind of measurement with entangled photon pairs or something?
Yes.
Oh, for general, I think, for any quantum state. The Heisenberg limit is the maximum, right? I don't think there's like a super Heisenberg limit.
No, there's no super Heisenberg.
Yeah, so that's like the maximum.
Bound.
That's the bound, yeah. For any measurements that you could do, yeah.
Oh, okay.
Yeah.
If you can get like the best state possible.
Okay.
Using the best measurement possible. Yeah. And you know, people might say, well, why aim for that? Since like obviously if you but from the practical perspective, why not just like either use high power laser or just repeat your measurement until you get to the position that you want. Which in a lot of practical scenarios, that is true. In everyday life, you don't really need the kind of quantum enhanced metrology, but if you so happen to be working at the limit of the power threshold of your hardware, for example, in the case like gravitational wave detection, where they're already putting a lot of power inside their system, and they're kind of also fighting the noise that's coming from using a lot of that power, then actually getting a boost of that position without having to increase the power and also increase the time that they have to do it, because you know gravitational wave comes and then it goes, so you can't actually repeat your measurement. Then having that quadratic boost would actually kind of help them to perform that detection in a more regular basis. Like they can do it now without really having to have that quantum enhanced metrology, but they're only able to detect like really high energy events. So they're not doing their signs as regularly as they want to. And actually, as kind of a side historical note, the field of quantum metrology actually started out from gravitational wave detection, because Carlton Case kind of calculated how, like, a squeeze state, like by using that squeezing, we actually improve the precision of the gravitational wave detection. And that's how the whole field got started. In kind of more easily to envision, I would say, since in a more lower intensity, you can imagine if you're doing, say, biological imaging, if you dump your power a little too hard inside your imaging system, there's a lot of chance that you're going to destroy your sample, simply because, you know, a biological sample is actually sensitive to the power you're putting in, and you have a lot of chance of frying what you have inside the microscope. And also sometimes your sensors simply have spatial restriction. You know, there's now a lot of proposals for doing magnetometry using NV center, which is great because you can have spatial resolution from having such a small sensor, but with spatial resolution comes with the fact that you can't really have a lot of NV centers concentrated in a small space. So you have to work with the small resource that you have, but trying to get as much precision as possible given that small amount of resource. Okay, so that's kind of slight detour, just to give you some context of why people are interested in quantum metrology. Now let's kind of get back to how you can get to the control policy. So now we have a clear control goal here, is that we're trying to get a policy such that we're breaking the standard quantum limit, but we also want to add some practical constraints into this problem. We want to look at it when the noise is present. We're going to look at this when n is relatively large, and I want to put relatively here because we're still looking at n when it's countable. So it's not large in like the gravitational wave detection sense of large, when it's like in tens of thousands. We're just talking up to 100, that's all. And we're not restricting, and we're not giving any kind of a priori knowledge about the unknown parameter, so it can be anything about 0 in the domain of 0 to pi. So again, just kind of give you an overview here that in this problem, there have been people who look into how to do this in the model-based way. And the work that this project kind of builds on is actually the work that's done by Dominic Burry and Colin Wiseman, PM supervisor, actually. This work is kind of like I think it's out 2000 or something like that. So the idea behind this work is like people have taken it to the next level by now. But because our system is based on their system, we kind of like, okay, let's take kind of this, what they did, and then compare our work to theirs. So in their case, the model that they use is the model of the state evolution given outcome of the measurement, and the way they do control is that they use Bayes' theorem to actually update the distribution of the estimate. So you start out with like not knowing anything, so that's a flat uniform estimate. For every time that you have an outcome that is updated, and you get a sharper distribution that comes out, and then the control, like the controllable degrees of freedom, is updated such that distribution is minimized each time. And then the estimate at the end is calculated from a maximum likelihood method, but their method doesn't actually take into account noise or loss. So a good way to see how the method works would be well, they don't account for noise or loss. Let's see, if we actually put in noise, how would their method still work? Because that's one thing that like control engineer people always worries about. What if the model used doesn't match the dynamics? What would it still work? Would it still be okay? And we wanted to compare to the learning method that we use. So what we're going for is a completely model-free way of devising the policy. So we're using reinforcement learning to basically test out the policy through trials and errors. And the only thing the controller keeps track of is the number of photons that's going through. So we don't keep track of the history of what the outcome has been. So it just sees the outcome at that time step and then it moves on. It just reads the number of photons that has to go through, so it knows which part of the memory it has to use. That's all. And then at the end, it infers the value of the estimate by just reading out the value of the controllable degrees of freedom. Okay. So I don't think we really have time to go into the reinforcement learning part. So I probably have to skip this, unfortunately. Okay. I kind of want to show this slide because this shows how we represent the policy. So kind of the method that we use in reinforcement learning is called policy search. So that's not the method in reinforcement learning that you're going to see necessarily from, let's say, how people would solve, like, let's say, playing a game of Go, for example. And that's mainly because in those kind of problems, you can see all the state of the Go problem, of the Go board all at once. But in problem like phase estimation, we don't actually have the value of the phase. So that's more similar to how a robot would navigate inside a world, because they have to observe the world, but they don't necessarily see everything inside the world. And so policy search is a way that people implement reinforcement learning or reinforcement learning inspired. If somebody here doesn't like policy search as a method in reinforcement learning. And the way they do it is actually they would give the policy a structure that is suitable for the problem. So in this case, we kind of look at, okay, so what kind of decision does the controller have to make? So we know that the controller is confronted with a decision that can be represented as a binary tree, because they always get an output that is either 0 or 1. So it has to decide what to do. There's only 2 things they have to decide at any given step. So this is what they have to decide to do. So what's left is that, so what are the 2 things in each step that we want it to be? So Alexander Henschel, who was a PhD student with my supervisor previously before I come in, figured out through a lot of work that actually this kind of decision works with this problem. So what the controller actually has to do is has to decide whether to add or subtract a certain amount of phase away from the controllable phase shifter. What left to be optimized is how much of this phase has to be add or subtract. So the policy parameter here actually is a vector of size n, which is actually good for us because that means it doesn't scale exponentially with the tree anymore. It scales linearly. And if we want to go like push towards 100 photons, that's still very large for an optimization problem, but at least kind of doable. So Alexander Henshaw tests this out using particle swarm optimization. He also tests it out with noise as well, but it runs into a stagnation after like 45 particles.
A quick question. Even though the policy number is n, which in this case the upper bound is 100, but how many times you need to iterate the policy phi n until you get convergence?
To get convergence, around 10 times n square.
Okay, that's still much better.
Still make the algorithm scales with high n, but at least it's polynomial. Yeah, okay. And so when I come in, we were trying to do away with the problem of stagnation. So that's the evolution kind of drops off here. So what I try to do is try to make differential evolution, which we know by then is a promising algorithm because differential evolution works very well. It's one, I would say, one of the algorithms that can work very well at high dimensional problem, but it's terrible with noise. So we kind of have to figure out a way to make differential evolution work with noise for our problem, because all noisy problems can be different. And then we also test out kind of stochastic hill climbing just to see for sure if that greedy algorithm is not outperforming us in any way. And also the other thing that we did, because we also have model-based algorithm that has been done previously. So what we wanted to actually also do is compare the policies that we're getting from the model-based and the model-free method and see actually how we're doing in comparison to the model-based one. So again, I was looking through control textbook to see how control engineers were doing this, because they were doing this for classical systems before. As it turns out, their kind of performance measure they were looking at were not quite relevant to quantum control problems, because they were looking at performance in time. In kind of our problems, performance in time is not relevant. So we have to kind of look into what would be the relevance measure that we're looking at. Performance definitely is kind of the number one thing we want to look at, but also robustness. But we also have to think of what do we mean by robustness? What is the robustness to us? And we want to look, the other thing we kind of want to look at is, what about the resource that we're using? Is there anything important in the resource that we can talk about? So the resource for devising, so the resource in the supervisory controller, and the resource in executing the policy, so the resource used by the controller. So because these two controllers can be thought of as specialized computers. So you can use time complexity, you can use space complexity from computer science to actually do those kind of calculations. Okay. So in robustness test, what we did is, so our optimization algorithm, our controllers in the simulation obviously are ignorant to the noise we're putting in. Great. So now we're putting in different noise models into our simulation, different levels of noise as well. And we're looking at, so what are the variants of these noise when those controllers start to struggle to get to the start to struggle to break the SQL, and see basically who stopped breaking SQL first and where they stopped breaking. So this is a very old result, I would say, but this kind of gives you an idea of what kind of results we're looking at. So this is a log plot. That is why you're seeing the the power law scaling as a straight line. So that is a hypothetical Heisenberg limit that we never reach. But we are able to break the standard quantum limit. That is actually a line that we generate using the product state. And the rest of the lines are the lines that we get from using an entangled state. So it's the same state that is used by Berry and Weisman. So we're trying to use the same parameter, the same condition that we're using, having only the policy or the way we're doing the control as being the only thing that is different between the two systems. So as you see here, the PSO stagnates, but CE keeps going. And with noise, you kind of see that as we added noise, the uncertainty starts to go up. And hill climbing, the greedy algorithm, also stagnates really fast right here. And it doesn't mean that differential evolution doesn't stagnate. It does. And we see the stagnation around, n equals 90, but we add a criteria which allows it to continue to optimize until it managed to get that straight line again. But of course, that increased the resources, the computational resources it has to use to do the optimization. That's why we want to start with a really good optimizer to begin with before we add his accept reject criteria. And that's why we don't add it to the particle swarm optimization, because we have to start pushing it at 45, as it's going to take a lot of time. Okay, so that's kind of what the type of result we're seeing. Now we want to look at what happens when we start changing noise models. So there will be a lot of lines, so that's not super informative. We'll have a summary table later. So this, I just want to show you that these are what we get from the learned policy. These are what we get from the model-based Bayesian control. So they are also breaking the standard quantum limit, despite despite their model not matching up with the dynamic. So they're actually doing very well for themselves. Although in their case, when the number of particles are very small, they're struggling quite a lot. But once the number of particles get large, they're doing very well.
I think I was missing V. I'm sorry.
Yeah, go ahead.
Yeah.
I think I was missing the definition of V. What is V again? Sorry about that.
V is the variance of the noise we're adding.
Okay, and this is a noise. Is it added to the policy search, or maybe I was missing some important parts earlier? I'm sorry about that.
Oh, I was rushing through it actually. So V is the variance of the noise model we're adding to the simulation of like we're adding to the Mach Zehnder interferometer.
Oh, okay.
Yeah, so add this to the phase difference.
Okay.
Oh, you mean noise to the phase?
Yeah.
Or the actual phase that you want to estimate?
Yeah, you can think of it like that.
So there's like the real model-based dynamics behind the scene, and then you add this kind of noise to that model to compare whether reinforcement learning will learn the distribution.
Yeah. So the reinforcement learning one also see the same kind of noise, except they would see the data that's generated by the Mach Zehnder with the noise.
I see.
Yeah. So they have access to that data, but the model-based one would not. They have the same response to when they don't have noise.
Okay, I see.
But then from this picture, like for example, well, the C and D and J, none of them get better than the standard quantum limit, right?
Well, actually, it's really hard to tell from here. Well,
because I guess above the line or something.
Yeah. Well, in terms of like the uncertainty itself, it doesn't drop below the sign. But if you look at the scaling, let's say, so this one is when they actually do the fitting for the scaling, and this is like the scaling for the high end, so like towards the end of the data. You will see that actually they were doing pretty well. So the last two columns are the one for the Bayesian, and column 3 and 4 are for the learning policy. So for normal noise, let's say, Bayesian just breaks the standard quantum limit all the way through, up to like B equals 4.
For the Bayesian inference, do you assume the prior to have the same type of noise, or are there more general way without assuming the type of noise?
Can you repeat the question, please?
When you do Bayesian inference and get like really nice, even breaking the standard, not breaking the Heisenberg limit kind of thing, do you need to assume the noise is that particular type? Like if you simulate with normal noise, then do you assume Bayesian prior for the normal type of noise, or are there more general method without assuming the type of noise prior?
So for this one, the Bayesian method doesn't assume any noise.
Oh, that's interesting.
Yeah, that's interesting. Yeah, that's interesting because the usual assumption in control theory is that if you don't put in the noise for the model-based stuff, it should break. This one doesn't break. So we're like, huh.
That's interesting.
And if anything, they're doing comparatively similar to the learn policy. Well, slightly worse if you look at the log normal noise, but they're doing very well with the normal noise.
But I guess the trade-off is in the complexity, right, as you highlight below.
Yeah, the trade-off is very clear in the complexity, because in the learn case, because we kind of assume the like in the learn policy, we kind of assume the structure and assume how the controllable phase shifter should be computed beforehand. The scaling is much smaller because there's no model that needs to be computed live during the update. Whereas in the Bayesian case, you have to compute the model, you have to compute the update, so the scaling is worse. But of course, then you have to like in the learning case, you have to sacrifice the learning time, which is a high end, and a lot of experimentalists seeing that would kind of go, oh no, that's might not be doable. Which had happened when we talk to experimentalists, that had happened. So actually, talking about why the Bayesian was doing well, comparatively well with the learned policy here, one thing that kind of come up during the discussion is that maybe in this case, the input state might have been a factor. because the input state that we picked, we found out that it's actually robust against loss. So we're not entirely sure if it's also robust against noise. So that's something that's kind of a question mark for this particular problem. We didn't really have time to investigate further.
Can you repeat the remarks again? Sorry, I was missing.
Yeah. So one thing that's kind of common between both the Bayesian control scheme here and the learn control scheme here is that we use the same input state for the phase inference. So it might be that the reason they're both robust against the change of noise is that the input state they're using are both robust. So there has been work in quantum metrology that's showing that some classes of state actually preserve the information of the things they're inferring better than other states in the presence of imperfections, noise and loss and things like that. So it might just be that this is just a really, really good state in those situations.
Mm-hmm.
And so the control, although the control definitely kind of adds something to it because we see that there is a difference in the normal noise there, it's not like that big of a deal in this case.
So when you say input states, what do you mean? I'm just a little confused. So your input state is the state that you want to estimate, right? Which has noise on it, right? Am I right?
So what I kind of mean is that so I don't remember exactly which paper, but there's a paper that came out that said that some of the state actually preserve Fisher information better than others.
Okay.
Yeah, even though that it might have gone, like some state goes through noise and then the Fisher information would drop. But then some states go through noise and then the quantum Fisher information that comes out actually doesn't drop all that much.
Okay.
And that was one thing that we didn't have time to actually really have a look at.
Right. So you just use like a one particular state in here in this work and not exploring different things. Okay.
Yeah. And it's the same state that Dominic Berry and Howard Weiss.
What is it? It's like a just total maximal.
Not really. It's a weird looking state.
I don't know about that.
That's the one. I didn't write down the full equation for it because it's really long. It would take like at least 2 lines of that.
Okay.
But it looks kind of like a truncated Gaussian, really squeezed Gaussian state. That's why it's really good with loss.
Okay, so that's the plot of C. As the coefficient in front of n. Interesting. Okay, thank you.
No problem.
Tip.
Yes?
What time is it? Like, can we push it further, or do you want to finish it on time?
I think we're already running.
Yeah, we're almost done. We have until 11:30, but we can discuss offline.
Sure.
Question and answer as well. It's like one quick remark. I'm quite surprised that the complexity of policy space for reinforcement learning is only ON, because I would imagine you have to do like tedious search, but somehow it was only ON.
ON is so the way we define policy space here is like the size of the array that need to store the information for it.
Oh, okay.
So if the search space, the search space itself is, if you're asking for the size of the dimension, it is still n. But
like, for example, the binary state is 2 to the n, but then the search space is much smaller than that for some reason.
That's because we impose a structure to it.
Right.
Yeah. It's that comes with a sacrifice in performance, though, because as you can see that even with no noise, we're performing worse than the Bayesian policy.
And also one remark, like on personal notes, I tried genetic algorithm before, which is kind of like dark arts. I don't know how you manage to find the optimal policy from differential algorithm that you mentioned. And I mean, do you have like specific ingredient for it to converge fast, or do you need to do trials and errors, try various parameters and so on?
Oh, it's trial and error, to be honest. And I don't know, personally, I kind of started out, like, if possible, look kind of at the distribution of the fitness, like see what the distribution of the population looks like at some measure. Because in some problem you want it to actually converge slowly at first.
I see.
Like that.
I see. Okay. Yeah, it seems to be you have to play around a lot with this kind of things, right?
Yeah.
Right.
It is dark art.
Right. And then one comment on this particular slide, it appears that for large variance, random telegraph and log normal, the model-free method seems to work better for inference of the noise. Right. Have you looked at other fat tail distribution for noise? Because it appears to me, perhaps it's due to the large deviation tails, that's why the standard assumption of Bayesian breakdown and didn't perform so well.
We haven't got a chance to do that, actually. That is a great observation.
Yeah, because I don't know the detail of this Bayesian update, but typically they assume some finite variance and the tail is truncated at some values, but I don't know. I haven't looked into the literature, but it appears to be so. I don't know.
Thank you. Okay, actually that's pretty much the end of the talk. This is just like a few directions that comes out of the project in regards to like the direction of where we can take with RL control. So some of the things that comes out from that from the project is like from the project I've talked to some of the computer scientists about RL and this problem, and I kind of mentioned a little bit before that there are computer scientists who's not very happy with me calling a policy search method a reinforcement learning, and that's because to them a reinforcement learning is a method which you update the learning at each step of the action instead of like doing this at a large episode. As a physicist, I would say I do not go into this argument. I would leave that to the computer scientists to figure it out upon themselves. But that does raise a good question, because the reason we have to stick to this kind of method is because the state that we choose, which is a good state from a quantum enhanced metrology perspective, give us no information for stepwise learning. So we don't know yet how much this characteristic generalize to other kind of quantum feedback problem. So that might be something to keep an eye out, because that does affect the kind of reinforcement learning we might be able to implement on quantum feedback control. And also, another problem would be like, what are the characteristics that would make RL performs better than the traditional optimal control? Because obviously, from this problem, we kind of perform comparatively okay with each other. So not all quantum control problem is going to benefit from just switching learning. So that's another thing to keep an eye out. Also, as I kind of mentioned, model free and model based are not two mutually exclusive things. You can kind of combine them together to reap the benefit from each other. Mostly to kind of reduce the learning cost and then get the flexibility of the data. And that's kind of one thing to think about if we're trying to kind of push towards like more practical, near-term control, quantum control research. I would think, at least personally. And again, like all this I kind of mentioned before, is that generating like the state for adaptive phase estimation is something I'm personally interested in. Nobody knows how to do it. Would learning be useful actually to kind of figure out how to do it? Because this, like, I don't know if there is a fundamental problem in trying to generate the state, or is it just a problem of human imagination, basically. And that pretty much concludes my talk. Thank you very much for your attention.
Thank you very much.
Thank you.
That was a great talk. I think we open the floor for questions now.
Yeah.
Thank you again.
Thank you.
You kind of work on many different areas and combine them all together. That's quite impressive.
This is why my PhD takes 6 years.
Are there any questions from the audience? You can unmute yourself and ask questions.
ภาษาไทยก็ได้นะคะ
It's true. Question จากใครก็ได้ที่ไม่ใช่4 คนหลัก
ใช่สงสัยจะอายกัน
บังคับเปิดวิดี
บัง
โอ
คับเลย
แต่เสียดายมีอยู่พาร์ทหนึ่งที่ว่าไม่ได้ฟังตรง machine learning
ต้องสกิป
ถามคำถามเยอะไปหน่อย
แต่ตรงนั้นอาจจะเทคนิคเกินไปนิดนึงเหมือนกัน
แล้วเดี๋ยวไปแยกคุยกันก็ได้ไหม
ใช่
แต่ว่าน่าสนใจเพราะว่าเราอาจจะมีโปรเจกต์ที่น่าสนใจด้วยแหละ
ได้
Oh, actually, no, we have Hirado. Is Hirado still here? I think he left. Tia, what? I think Hirado is here, right?
Yeah.
Okay. Yeah, so Hirado is actually also worked with Howard Weizmann. No, not right. He's a senior postdoc in Griffith, and he is also interested in this kind of like estimation and machine learning. Any questions, audience? Okay, if there's no questions, can I ask Pantita to like, maybe we could do in Thai. Is there anyone that is not Thai here? I'm sure. I'm not sure. Because Hirata was here. But no,
I think all are Thai. Yeah, all Thai people now.
ก็พูดไทยก็ได้ค่ะ แต่ว่าอยากให้อธิบายตัวพาร์ทที่สกิปไปสั้นๆได้ไหม
พาร์ทที่สกิปไป
แต่ว่าตัว reinforcement learning ก็คร่าวๆอาจจะไม่ต้องลงตรงนี้ก็ได้นะ
จริงๆก็
ว่าเลยค่ะ
จริงๆก็แค่คร่าวๆว่า reinforcement learning มันเป็นตัว paradigm ของ learning ที่เอเจนต์ต้องเป็นภาษาอังกฤษแล้วกันนะคะเริ่มมึน
yes it's fine whichever like easy for
ไม่
you
อย่างนั้นมันจะไทยคำอังกฤษค
ก็ไม่เป็นไรนะ
ำได้เหรอ
เป็นเรื่องปกติเป็นเรื่องปกติอยู่ในฟิสิกส์ทำอย่างนั้นไม่ได้ก็แย่อะ
จริง
ลองถามนักเรียนผมได้เทอมที่แล้วสอนนี่ไม่รู้จะพูดภาษาอะไรงง
เราจะค่อยๆทำให้นักเรียนชินกับภาษาอังกฤษมากขึ้นเรื่อยๆ
ใช่
ก็ตัวนี้คือแค่อธิบายว่าตัว reinforcement learning เป็นตัว paradigm ใน learning ที่ตัว agent ที่เรียนรู้อะค่ะจะต้อง interact กับสิ่งแวดล้อมคือมันจะไม่เหมือน supervised หรือ unsupervised learning ที่ว่าตัว agent เนี่ยเป็นคนเก็บ data เองเพราะอย่าง supervised หรือ unsupervised เนี่ยคือ data มันสามารถเก็บไว้ให้ล่วงหน้าแล้วเขาก็แค่อ่าน data แล้วก็เรียนจากตัวสถิติของ data ก็ได้reinforcement learning มันจะต้องออกไป interact เองแล้วก็ปัญหาซึ่ง reinforcement learning จะ solve เนี่ยส่วนมากจะโมเดลได้โดยใช้ในทางคณิตศาสตร์เขาเรียก Markov decision process ก็คือมันจะเป็นปัญหาซึ่งมันอาจจะมีสเต็ปของการตัดสินใจ1สเต็ปหรือมากกว่า1สเต็ปก็ได้ซึ่งตัวเอเจนต์เนี่ยหลังจากทำการตัดสินใจไปแล้วเนี่ยก็จะได้ response จากสิ่งแวดล้อมเนี่ยเป็น random response กลับมาซึ่งreinforcement learning เนี่ยก็ส่วนมากก็จะรู้กันว่าเอาไปทำอย่างเอเจนต์สำหรับเล่นเกมอย่างโกะหรือว่าอย่างหมากรุกหรืออะไรพวกนั้นแต่ว่าก็ในทางแต่ว่าก็มีคนเอาไปใช้อย่างเช่นในการสอนหุ่นยนต์หรืออะไรพวกนั้นด้วยให้สามารถ navigate ในโลกภายนอกได้ซึ่งก็มีความแตกต่างคือ2ปัญหานี้มีความแตกต่างเล็กน้อยที่สำคัญ ซึ่งอธิบายไปนิดนึงแล้วก็คืออย่างในเกมโกะเนี่ยเรามองเห็นตัวบอร์ดทั้งหมดเราสิ่งแวดล้อมของเราเห็นทุกอย่างคือในทาง reinforcement learning แต่ว่าเราใช้คำว่า state คือ state คือ state เนี่ยแปลว่ารวมทั้งตัว agent สิ่งที่ agent รู้แล้วก็การมองเห็น environment เนี่ยคือทั้ง2อย่างเนี่ยชัดเจนเคลียร์มองเห็นหมดแต่ว่าอย่างของหุ่นยนต์เนี่ยคือเขาจะต้องมองโลกภายนอกผ่านเซ็นเซอร์เท่านั้นดังนั้นมันแค่มองเห็นแค่บางส่วน partially observable ดังนั้นมันก็เป็น2ปัญหาซึ่งคล้ายๆแต่ว่าไม่เหมือนกันสักทีเดียวและแล้วนอกจากใน adaptive phase estimation แล้วเนี่ย RL ก็มีคนเอาไปใช้ในปัญหาอื่นในquantum control แล้วอย่างเอาไปทำ circuit design อันนี้เป็นงานในกลุ่มของ Hans Begel ก็คือลองดูได้ค่ะก็มันดีอันนี้ไดอะแกรมนี้จริงๆแล้วเนี่ยเขาพยายามแปะ scenario ต่างๆที่เขาต้องวางแบบเกตตัวไหนลงไปตรงไหนในเซอร์กิตดีดูแล้วก็แบบอะไรเนี่ยหรือว่าเอาไปใช้ในการดีไซน์ตัวเกตเลยก็ได้ว่าอันนี้งานนี้ก็ตัวนี้ก็สนุกดีค่ะเป็นการเอาไปใช้ในการหา control pulse สำหรับการทำ quantum sensor แต่ว่าเซนเซอร์ตัวนี้เนี่ยคือ dynamic ข้างในมันเป็น quantum chaos ดังนั้นคือการใช้ตัวโมเดลเองเนี่ยในการหาตัว control pulse เนี่ยคือมันยากเนื่องจากมัน sensitive กับค่าของ parameter มากดังนั้นเขาก็เลยใช้ RL ในการ test ตัว pulse แทน
เซอร์กิตดีไซน์นี่น่าสนใจมากเลยสุดท้ายมันแตกออกมาเป็นนอนแต่ละนอนี่คืออะไร
มันเป็นนอนแต่ละหนอนี่คือในแต่ละ time step ค่ะเขาจะวางตัวเกตลงเป็น1ตัว
มือนสมัยที่มีคอมพิวเตอร์ยุคแรกๆเนาะยุคนั้นดีไซน์ชิปเขาก็ทำ optimization โดยใช้ simulate annealing นะ IBM ใช่ปะแล้วตอนนี้ก็เปลี่ยนมาใช้ RL แทนแต่ว่าเป็น quantum circuit แทนใช่ไหม optimization นี่เป็นmagic สำหรับทุกยุคสมัย
optimize ก็เคยมีอาจารย์สอน engineer เขาบอก optimization ก็คือทุกอย่างนั่นแหละ โอเคค่ะ
ใช่
แล้วก็ RL จริงๆก็แบ่งเป็น2 approach ใหญ่มากแล้วก็เหมือนเดิมแหละค่ะ2 approach นี้ก็ไม่ได้มีตัวนี้คือสื่อต่อกันแล้วก็สามารถเกี่ยวขาแกว่งหากันได้อีกเหมือนกันอันนึงคือเป็น value based approach อันนี้ก็วิธีการของ value based approach คือแทนคือยกตัวอย่างเช่นอย่างในการเล่นเกมเนี่ยเขาก็จะ evaluate ตัว state แล้วก็ให้ค่าว่า state ดีหรือไม่ดีควรจะอยู่ใน state หรือเปล่าแล้วส่วนมาก action เนี่ยก็จะถูกไกด์ด้วยการดูว่า state ข้างๆเนี่ย state ตัวไหนดีดังนั้นตัวแบบนี้เราก็อาจจะไม่เห็น policy ตรงๆแต่ว่าเราก็จะรู้ว่าถ้าเราอยู่ใน state นี้เราควรจะไป state ต่อหรืออะไรประมาณนั้นแต่ว่าแล้วก็อีก approach หนึ่งก็จะคล้ายกับที่เห็นทำไปก็คือเป็น policy based อันนั้นคือเรา evaluate ตัว policy โดยตรงว่าเราจะใช้รูหน้าตาแบบเนี้ยเอาไปลองดูถ้ารูนี้ไม่ดีก็เอากลับมาเปลี่ยนรูใหม่
แต่ว่าดีไม่ดียังไงก็ต้องใช้ value base ต้อง evaluate measure อะไรบางอย่างดีไม่ใช่หรอ
ใช่คือทั้งสองอย่างนี้ก็ต้อง evaluate measure เพียงแต่ว่าเราจะ evaluate เอาไปแตะค่านึงกับอะไรมากกว่าแต่ค่านึงกับ state แต่ค่านึงกับ value policy
โอเคสิ
ตอนแรกที่ไปอ่าน literature พวก reinforcement learning ก็งงกับศัพท์ชอบใช้ศัพท์ประหลาดจริงๆคนที่ทำ stochastic process อย่างเงี้ยมันคุ้นเคยอยู่แล้วเพียงแต่ว่าศัพท์มันจะใช้ประหลาดแบบ action มันก็คือการ take state ที่เป็นไปได้อะไรอย่างงี้ policy ก็คือ transition rate matrix นั่นแหละ
เอาเหรอ
คือแบบศัพท์มันเหมือนกันเลยคือถ้า translate ได้ก็คือจบอ่ะ
ใช่
แต่ว่าตอนอ่านตอนแรกจะงง
ทำไมเราคิดนึกว่า policy เป็นมากกว่า transition matrix หรอเป็นแค่นั้นจริงหรอ
คือเหมือนกับวิธีการเลือกเดินแบบสุ่มอะไรเงี้ยถ้า option มันเยอะๆแล้วสุ่มยังไงให้เจอสิ่งที่มัน optimum เร็วที่สุดมันก็จะมีวิธีการดีไซน์ transition matrix หรือว่า policy นั่นแหละคือถ้าสมมติเข้าใจ dictionary translate ระหว่าง2ฟิลได้ก็จะ pick up ได้เร็วอ่ะ
แล้วมันก็มี translate ไปด้วยนะคะ control
ไป control นี่ยิ่งงงหนักเลย
นั่น translate แล้วเดี๋ยวนะคุยเรื่องเดียวกันแต่คนละภาษาคืออะไรอยู่บางทีทำสไลด์ให้อาจารย์ต้องนั่งถามอาจารย์เราจะใช้ภาษาอะไรอาจารย์
เวลาทำอย่างนี้เวลาเขียนเปเปอร์นี่ต้องดู audience เป็นหลักเลยไหมหรือว่ายึดติดยังไง
ต้องดู audience ก่อนเลยค่ะเราคุยกับใครก่อนเอาให้แน่ก่อนเอาจริงอันนี้คือพยายามแมปปัญหาเข้ากับ RL แล้ว
ใช่
พยายามดูว่า state คืออะไร action คืออะไร transition probability คืออะไร reward คืออะไรอันนี้อาจจะบอกว่าตอนทำเองงงมากอย่าง state เนี่ยคือเพื่อทำให้งงน้อยลงแล้วก็แปลว่าเอเจนต์เรารู้อะไรบ้างเอเจนต์เรารู้ว่าตอนนี้ n ที่ผ่านเข้ามามีกี่ n เพราะว่าเราต้องอ่านเข้าไปใน memory ว่าอยู่ที่ช่องที่เท่าไหร่เราต้องดูว่า n เท่าไหร่เรารู้ controllable ค่าของ controllable กับ shifter ได้จะใช้ไหมอีกเรื่องหนึ่งเรารู้ค่าที่ ตัว detector อ่านเข้ามาในสเต็ปนั้นคือเราไม่ได้เก็บค่าของสเต็ปอื่นๆเราเห็นค่าของสเต็ปนี้
อ๋อไม่ได้เก็บแบบว่า n น้อยกว่าไม่ใช่ n ก่อนหน้านั้นหรอ
ไม่ได้เก็บค่าเอง
คือ
อันนี้เป็นการตัดสินใจเลือกว่า control system ของเราจะทำแบบไหน
เคยลองใช้พวกออนไลน์ learning ไหมมันก็จะเก็บ history ตั้งแต่สเต็ปแรกไปถึงสุดท้ายแล้วมันก็จะคล้ายๆ reinforcement learning แต่ว่ามันใช้ information มากกว่า previous step อะไรเงี้ยตรงนั้นเขาก็มีแบบ regret bound guarantee อะไรพวกนั้นที่ค่อนข้างชัดเจนว่า error มันจะเท่าไหร่
ไม่เคยลองเหมือนกันค่ะ
ครับ
ดูเดี๋ยวจะลองไปค้นดูค่ะออนไลน์ learning ใช่ไหมคะ
ใช่เพราะมันจะมีอัลกอริทึมที่เรียกว่า follow the regularized leader ที่คนเขาชอบใช้กันคือจะเก็บ cumulative cost แล้วก็จะให้มี exploration ผสมไปด้วยแทนที่จะแบบ maximize cumulative cost อย่างเดียวอะไรมันก็จะพวกนั้นข้อดีคือมันมี theoretical guarantee อยู่แล้วแต่ไม่แน่ใจว่าในกรณีนี้มีหรือเปล่าว่ามันจะเจอ error ได้เท่าไหร่อะไรเงี้ย
กรณีคิดว่าไม่มีอะค่ะ
ครับแต่น่าสนใจไอเดียที่ add noise ที่เป็น large deviation นะถ้าผมเดาว่าไอ้ Bayesian framework มันไม่สามารถที่จะ take into account large deviation tail ได้อาจจะเป็นสาเหตุหนึ่งที่ทำให้ telegraph noise กับอีกตัวหนึ่งlog normal มันมี error ค่อนข้างน้อยเทียบกับ Bayesian เนาะ
ก็น่าจะเป็นอย่างนั้นแหละครับ
แล้วมันจริงเฉพาะเวลา V ใหญ่ๆด้วยถ้าดูจากกราฟถ้าดูจากพลอตอันนั้นนะแต่ไม่รู้พวก large deviation noise ที่มันสำคัญแค่ไหน เพราะว่าส่วนใหญ่ noise พวกนี้มันน่าจะมาจาก measurement noise ใช่ปะโมเดลที่เขาใช้กัน
โมเดลที่เขาใช้กันส่วนมากเป็นนั่นเลยค่ะเป็น Gaussian noise
เป็น Gaussian noise เลย
ขอกลับมานิดนึง action นี่แปลว่าอะไรนะ
action คือสิ่งที่ agent ทำกับ environment ค่ะ
อ๋อโอเคถึงอันนี้ก็คือแบบลายที่2 bullet ที่2ก็คือ action เป็นไฟล์ n 1
ก็คือตัวสิ่งที่ทำกับตัว controllable descriptor
อันสุดท้ายที่จะถามคือไอ้ diagram อะค่ะ
อะไรนะคะอันนี้เหรอ
ใช่คือ
ค่ะ
เอาง่ายๆเลยคือหมายความว่าเริ่มจากไฟล์0แล้วก็0นะเป็นตัวแล้วออกไปเป็นลบเดลต้า1เดลต้าบวกลบเดลต้า1นี่คือแปลว่าอะไร
ไอเส้นสีแดงนี่คือเป็น demonstrate branch นึงที่เกิดขึ้นได้อะแต่จริง branch ลงมาอย่างเงี้ยคือมันเกิดขึ้นโดย random แต่ว่าการ select branch แบบนี้เกิดขึ้นจาก measurement result ที่เราได้มาซึ่งก็ random
คือขาคือขาก็คือแตกออกมาด้วย measurement result
ใช่
แต่แล้วเดลต้านี่คือมาจากไหนเดลต้ามาจาก
ตัวเดลต้าเองเนี่ยมาจากการ optimize ค่าของเดลต้ามาจากการ optimize
คือตัวไฟล์เหรอ where ไฟล์
เดลต้าเนี่ยเหรอคะ
เหมือนกับ
ไม่ได้ไฟล์
เหมือนกับเริ่มต้นไฟล์0เสร็จแล้วมี information เข้ามาdecision process มันก็ตัดสินใจว่าสเตทที่มันวัดมาเนี่ยเป็น0หรือเป็น1ถ้าเป็น0ก็ไปทางซ้ายเป็นลบเดลต้า1ไปเรียกว่าเป็น action ถ้าเป็นวัดออกมาแล้วมันเป็น1ก็จะไปทางขวาแต่อย่างในรูปนี้วัดสเต็ปแรกแล้วมัน decision มันเลือกไปทางซ้ายมันก็เลย measure เป็นสเตท0ใช่ไหมในสเต็ปแรก แต่แล้วพอมันได้ information ของสเต็ปที่2เข้ามามันก็ตัดสินใจต่อว่าสเต็ปที่2มันจะไป0หรือ1ใช่ไหมในกรณีนี้สเต็ปที่2มันเลือกไป1จากการทำ Markov decision process ก็เหมือนเป็น space time diagram อะ แต่ว่าแทนที่แกน x จะเป็นตำแหน่ง particle ก็เป็น state แทนแกน y ก็เป็นเวลา
แปลว่าตัวเดลต้าเนี่ยเป็นอะไรที่เกี่ยวกับตัวไฟล์ใหญ่ไม่ใช่ไฟล์เล็กคือมันมีไฟล์2ตัวมันจะมีไฟล์คือเดลต้านี่เกี่ยวกับไฟล์ใหญ่ตัวเดียวนะก็คือเป็นเป็นแอคชั่น
แต่ว่ามันจะเลือกไปลบเดลต้าหรือบวกเดลต้านี่ขึ้นอยู่กับไซน์เล็กด้วย
เอาเหรอ
ใช่ไหม
นึกว่าขึ้นกับ measurement อย่างเดียว
ขึ้นกับ measurement แต่ probability ของ measurement ก็
ขึ้นกับไฟล์
แต่มันไม่เกี่ยวกับว่ามัน interfere แล้วมันได้0หรือ1หรือเปล่า
ก็คือ probability ที่จะได้0ก็ได้1จะขึ้นอยู่กับoverlap ของไฟล์กับไฟล์ big file กับ small file ใช่ไหมใช่
ขึ้นกับ difference
มันมีที่คำถามหลับที่เรามิสไปตั้งแต่แรกก็คือว่าไอ้เฟสไซน์เนี่ยมัน affiliate ยังไงกับเจ้า quantum state sin n นะมันคือ exponential i phi เฉยๆเลยป่ะหรือว่ามันคืออะไรมันคือเฟสแบบนั้นป่ะหรือว่ามันคืออย่างอื่นอันนี้เรามิสไปตั้งแต่ตอนแรก
หมายถึง
ที่บอกว่าเราวัดเฟสหน้านี้แหละ
ใช่ไหมคะ
ใช่อันนี้มันคืออะไรนะไม่ค่อยคุ้นเคยไม่เคยทำผลตอนเด็กงง
อันนี้ตัว unitary มันคือ e กำลัง i ถ้าของอันนี้เลยนะคะ e กำลัง i ไฟล์ลบไฟล์ใหญ่เนี่ยค่ะ
โอเคก็คือเฟสตามความหมายของเฟสควอนตัมสเต็ปไป
ใช่ค่ะ
โอเคครับ